So the first thing we want to do when we're sketching the graph of a function is identify the domain of that function. And the domain of this function, it's a well-behaved function. Well, it's normally minus infinity to infinity, but what? I've restricted us to the domain 0 to 5 pi over 2. Does everyone see that? Okay. The next thing we want to do is we want to find the zeros. Hey, folks, this thing only has 1 0. Okay. If I were giving you this as a test question, I would probably make note of this. Note this only has 1 0. Okay. And in fact, we can find that 0 by inspection. What number, when I plug into this function, is going to output a 0, folks?
X equals 0?
Yeah, if I plug in a 0 into this function, it's going to output a 0. So x equals 0 is a 0. Folks, you can actually, and now that I'm thinking about it, I'm going to make a new question for people later on. You can actually use calculus to show that there's only 1 0 to this problem. Okay. But another way you could, and sort of in that line, at x equals 0, both this function, x, is increasing, and this function, 2 sine x, is increasing. This function stays increasing forever. Its derivative is always positive, the positive number 1. This function will eventually start decreasing, but it will never take you back down below to the x-axis again. It never gets down low enough. Okay? And you could make an argument on that if you wanted to, but for right now, let's just assume f has only 1 0. Okay? All right. So that's the one part about this particular graph where I'm fudging things a little bit. I'm letting you guys assume that it has only 1 0. You could do some more work to justify that. Okay. The next thing is always to find the y-intercept. Of course, what's happened in this case? We've already done the work to find the y-intercept when we said that x equals 0 is a 0. Folks, there's a lot of times there's some redundancies in this graph, in this process, and sometimes there's steps that don't really apply. Okay? So the next thing we go do is we look for our vertical asymptotes / holes. There's none. Why not?
It's continuous.
Good, I'll take that. You can actually relax that a little bit, Cole. You don't need to say that it's continuous. Well, actually, no, I'm sorry. Cole, you're exactly right. You have to say that it's continuous. When we identified the domain, though, notice we had no exclusions in the domain, and we should have really said that there are no breaks in continuity either. Okay. So great. Yep, you're exactly right. Good. Then what about the long-term behavior, folks? The long-term behavior / horizontal asymptotes / oblique asymptotes. What do we typically do when we examine the long-term behavior, folks? And just a typical question.
Use limits as you approach infinity and negative infinity.
We take the limit to infinity to figure out the far right behavior, and we take the limit as x approaches negative infinity to figure out the far left behavior. Okay. Well, what? What's my domain on this function?
0 and 5 pi over 2.
Yeah. So does it make sense to look at the limit as x is approaching infinity or as x is approaching negative infinity? Yeah, so this is not applicable in this problem. Because we've restricted ourselves to some other domain. We okay with that, folks? All right. Okay, so then we go find the first derivative, f prime of x, that's equal to 1 plus 2 cosine of x. If we set that equal to 0, that's going to happen when the cosine of x is equal to minus a half. Go thinking about your unit circle, folks. Where is the cosine value equal to minus a half? It's equal to minus a half here and here, on the angle from 0 to 2 pi. Careful though, our domain's a little bit bigger than that, so we could potentially have more locations. So I think that we've got that the cosine will be equal to, let me make sure I've got that graph right. Yep. Will be equal to -1/2 at x equals 2 pi over 3, x equals 4 pi over 3, and would also be equal to -1/2 at where? If you kept going, let's see if we added 6 pi to that. 6 pi? Yeah. That would be at 8 pi over 3. But notice that we're now outside of the interval that I gave you. So those are our only two critical numbers from the first derivative. Okay. Now we're going to go ahead and take the second derivative of this function. And that's equal to -2 sine of x. And if I set -2 sine of x equal to 0, folks, again, as we go further along, I'm going to be reminding you of less and less. So folks, one thing that in my head I just checked before I even did that is I asked, where is the second derivative undefined? Okay, that's part of being a critical number, right, is where the second derivative is undefined. But this is defined everywhere, so I didn't even make mention of it. Okay? So as you go further along, we're going to be a little bit less picky about things, but you have to know as a calc student where you need to be careful. Does that make sense? Give me a thumbs up, thumbs down, deer in the headlight. Give me something so I know how we're doing. Thank you, thank you. So let's see here. Where is the sine of x equal to 0? It's equal to 0 if x is equal to 0. In fact, we could even write a bunch of these. Let's go ahead and write minus pi, 0, pi, 2 pi, 3 pi. But what? This one, and this one are not in my interval. Right? The only place where the sine function is equal to 0 on the interval 0 to 5 pi over 2 is at those two locations. Okay, so now we're ready to go make that chart. Okay, what goes on the chart? Any exclusions in the domain? Well, this is defined everywhere we're working. Okay. But we should also put then, because it's got endpoints, we should put endpoints of the domain on there. It is critical that you not take test points from outside your endpoints, certainly. And you really don't want to use the endpoints either, because you can get some misleading information. So you've got to take something from in the middle. Then we're going to put all of our critical numbers of the first and second derivative on here. So we've got this critical number at 2 pi over 3. And then we had another critical number at pi. And then we had a critical number at 4 pi over 3, and then we had another one at 2 pi. Whew, that is a big list of intervals to be checking. Okay. So then I need some test points. Okay. Be judicious. Be thinking about what you want to pick. What's easy to evaluate in your trig functions? Certainly pi over 2 is one of the easier ones. Okay. And if it helps, draw a unit circle to help you. Yep, so let's see, we've got this critical number here, this critical number here, this critical number here, and this critical number here back at 2 pi. And make sure you're taking the right test points. So I think I'll use 3 pi over 4 as a test point. And I think I'll use 5 pi over 4 as a test point. So I picked a test point. I picked this one right here. Let's see here, pi over 2. I picked this one right here, this one right here. Let's take 3 pi over 2 as a test point. And then I need something between 2 and 5 pi over 2, which is back up here. So I think I should take a test point right there. Let's take, we go around twice. Let's see, that's 8, I think that, so that's 8 pi over 4, so I think it's actually 9 pi over 4 there.
Did you mean to do 2 pi?
That's what I'm thinking too. Isn't that supposed to be 2 pi?
That is supposed to be 2 pi. Thank you, folks. Yep. And then I think here we want 9 pi over 4. So double check me that there. If I, let's see here, if I divide 4 into 9, it goes 2 and some change. So that's that 2 pi around goes around the circle, and then it's 1 more pi over 4. So I think we're okay there. How are we doing, folks? So those are my test points, and this one's sort of a bear to evaluate. I understand, but you know, that's life. So let's see here. We're going to plug in pi over 2 into our first derivative, which is right here, 1 plus the cosine. Well, pi over, that's positive, so we're increasing. The cosine of 3 pi over 4 is minus the square root of 2 over 2. The 2's cancel. This factor of 2 will cancel with that 2 in the denominator, which gives us minus the square root of 2 added to 1. We're going to be decreasing there. If we plug in 5 pi over 4 into this function, that's kind of the same story because the cosine value is the same there. So we're still decreasing. If we plug in 3 pi over 2, we're increasing. And if we plug in 9 pi over 4, we're increasing. Folks, I might have done that a little bit faster than you. That's okay. But go back and rehearse your unit circle a little bit and see how we were able to plug those in fairly quickly. Are there any questions on that? Give me a thumbs up, a deer in the headlights. I got to know how you're doing. Okay, good.
I do want to confirm something though, real quick.
Yeah, please.
The long-term behavior / horizontal asymptotes is like that whole process of taking the limit is only applicable if the domain is negative infinity to infinity.
Yeah, because what this is, when you're asking for the long-term behavior, it's saying like, as we go far to the right, what is the graph doing? As we go arbitrarily far to the right, how is the graph behaving? Well, our graph, we can't go arbitrarily far to the right. We have to stop at 5 pi over 2. So instead, we'll deal with the endpoints when we look for our global maxes and mins. Yeah. All right.
That helps.
Great. Great, great, great. F double prime of our test point. What is the second derivative going to tell us, folks? It's going to tell us about the concavity here, right? Whether we're concave up or concave down. Okay. So let's see here. If I plug in pi over 2 into our second derivative, that's going to be concave down. If we plug in 3 pi over 4, the sign there is... folks, hang on just a second. I disagree with that. We'd be concave down. Okay, if we plug in 3 pi over 4, we're still concave down. Come on, Braden. 5 pi over 4, concave up. 3 pi over 2, that's concave up. And 9 pi over 4, we're concave down. Thank you, folks. Okay. Let's make some conclusions based on our chart. Okay. And folks, I should have done this. I'm sorry. Why is 2 pi over 3 up here? It's because it was a critical number of f. Why is pi here? Because it's a critical number of f prime. Why is 4 pi over 3? It was a critical number of f, and this was a critical number of f prime. Folks, in some cases, it doesn't really matter whether you make the distinction between it being critical number of f or critical number of f prime as long as you interpret it correctly. But I am trying to get you guys to be careful about why you put things on these graphs. These were the endpoints, right? Okay. So this information here, looking at this chart, the information around around here, that's enough to tell me that x equals 2 pi over 3 is the location of a local max. Okay. Sure enough, let's see, if I plug that into, or not sure enough, but if I plug that into a calculator, that's going to give me the order pair 2 pi over 3, and then I'm just going to give a decimal approximation, folks. And I did this beforehand, but now you guys are all covering it up. 2 pi over 3, oh, I didn't do it. F of 2 pi over 3. I get about 3.83. We can also conclude, because of this information right here, that x equals 4 pi over 3 is the location of a what, folks?
Local min.
A local min. Great. And so if you were to plug that into a calculator, we get, just for a decimal approximation, because I mean, you get the exact answer, but it's a little bit hard to interpret that. Let's see here. If I plug in 4 pi over 3, I get 2.46. By the way, folks, when I was talking about how to reason that there was only one zero, that argument right there would help you get there. Okay. And then what else do we see? Well, looking at this information right here and this information right here, we see that we've got changes in concavity at places where the function's defined. So we've got that x equals pi and x equals 2 pi are inflection points, are locations of inflection points. That is, the inflection points for this function are the ordered pairs pi, comma, and this one's nice. When you plug in pi, it outputs pi, so about 3.14. And when you plug in 2 pi, it spits out 2 pi, so about 6.28. Okay. The other thing we need to do is we need to look for our global max and mins. And so we also need to evaluate f of 0, which is 0, and we need to evaluate f of 5 pi over 2, which is 5 pi over 2, which is approximately 7.86. Well, that's why that didn't matter. Folks, you don't actually have to make this graph bigger. I'm a liar. Holy shout. We spent almost 20 minutes on this problem, folks. Holy shout. Let's start putting all this information together. Okay. I like to start in the order in which I put it on the chart. So I'm going to go put my 0 here at 0, 0. Okay.
Charles, I'm not convinced that your 5 pi over 2 is correct. I keep getting like 9.85.
I agree. I agree. I made a silly assumption in my head as I was doing that. 9.85. Great. I agree. Thank you. Everyone see there's a mistake there, folks. I just too quick. I thought I could just check 5 pi over 2 and get a decimal approximation of that. I forgot that the sign at 5 pi over 2 was 1, and so we had to add 2 to our answer. Yeah, silly mistake on my part. Great. Let's start putting all of this information together, folks. So we said, okay, something interesting was happening at 4 pi over 3. Let's see here. 1, 2, 3, 4 pi over 3 is right about here, and that was the coordinates 2.46. 2.46, so that's somewhere like right about there. That was a local min. We had 2 pi over 3 gave us 3.83, so there's 2.83, 3.83, so we're about right there. What am I missing, folks? that fact. 4 pi over 3. This is pi over 3, this is 4 pi over 3. Sorry, folks. This is pi over 3 right here. Or 2 pi, this is our 2 pi over 3, I mean. And so that gives us about 3.85. Pi, as an inflection point, gave us out pi, which is about 3.14. Right about there. And then 4 pi over 3 is right about here. There's 4 pi over 3. And that gave us 2.46 approximately. So right about there. Up a little bit higher there, maybe. Folks, everyone see what I'm doing? I know this is a little bit convoluted. I'm going through and I'm putting on our points, our key points that we found for this graph. Okay? And then we had one more inflection point way out at 2 pi, which is about 6.28. Okay. And then we plugged in let's see here, 5 pi over 2 as our endpoint, and we got 9.85. Let's see, where's 5 pi over 2? That's right here, I believe. Is that right? 1, 2, 3, 1, 2, 3. Yep. So that's up here. So folks, if we start putting all this together, all right, so let me get caught up here. Give you a chance to get caught up. We got these dots on the page. This is the part that I only get to. You see, these problems take me quite a while. They take us quite a while to do in full. I've got these key points on the page. Now I'm ready to use calculus to fill in the gaps. So this is where I want everyone to, if I kind of lost you somewhere, please don't worry, we can get that fixed. But this is where I need everyone's full attention. So, on the interval between 0 and 2 pi over 3, we need to be increasing in a concave down manner. You know what's coming up. Show me concave down. Where on a concave down interval are you increasing? That's this interval right here. So my graph needs to be behaving that way. It needs to be increasing in a concave down manner until I get to 2 pi over 3, where I have to have a what? At 2 pi over 3, I have to have a horizontal tangent line. Okay? And so I arrive at 2 pi over 3 with a horizontal tangent line, and then I'm going to start decreasing in a concave down manner. Concave down, decreasing, that looks like this. So we're going to be decreasing in a concave down manner. Okay? Now folks, do one thing to be a little bit careful of. This is an inflection point, right? We said that at pi we had an inflection point. Sorry, it's not quite exactly above pi, but we've got an inflection point there. We okay with that? So we've got an inflection point at pi. Folks, did we have a vertical tangent line there? So please be careful not to draw a vertical tangent line. Don't come straight down like that, right? That would imply that we had a vertical tangent line. So just be a little bit careful that you still have some sort of you're decreasing, but you haven't gone quite all the way to vertical yet. After we leave that inflection point, there was the inflection point, we're going to continue decreasing, but now in a concave up manner. Okay? So I'm going to try to clean that up just a little bit. Let's just try to clean that up just a little bit now that we kind of got the idea there. So there's concave down decreasing, there's concave up decreasing. Where did that change? At the inflection point at pi. And I know that's not quite right above pi, but bear with me. Okay. Before that, we were increasing in a concave down manner. After we leave this horizontal tangent line at 4 pi over 3, we're going to begin increasing still in a concave up manner until we arrive at the inflection point at 2 pi. After 2 pi, according to my chart, I'm going to keep increasing, but now in a concave down manner. And that's what we end up with. Okay. There's the graph of this function. So folks, let me just reiterate something I said earlier. Did we plot points to graph this function? Well, we graphed a few carefully selected points. Okay. Did I just build a table of values or take a calculator and just start plugging in a bunch of x coordinates into this function to find out what its graph looked like? No. Could you do that? Well, I guess if you're on a desert island, you got nothing better to do. But if you're learning calculus, you can't do that. Okay? That's not calculus. That's just plugging in numbers. I'm not interested in that. You shouldn't be either. You could have done that in algebra.